Hi guys. So I'm here to present about a topic which we acquired from CPLabs, which is CPU control unit operation. So first of all, I would like to thank Mr. Fidas for giving us this opportunity to do some research about the topic we acquired, the control unit operations, CPU control, to get a higher level of understanding about this topic. So first of all, I would like to introduce my teammates. So our team leader is Lim Jipeng and Zhou Weixin, Li Tianyong, Devaraj, and me, Eric, as the teammates. So I'm going to start my introduction about our topic. So nowadays, computers, laptops are very common in our lives. So every house will have at least one desktop or laptop in their house for their working purpose. So, however, people hardly understand how the computer works and what's inside it that controls all the work and help the programs to run, which is the CPU, and how the control unit inside the CPU works. So we're going to do some research about this. So from television, laptops, desktops, radios, they all, and blah blah blah, they all have all the CPUs to help them to run appropriately. And yeah, CPU is kind of like the master of these electronic devices, and control unit is the master of the master, which means the control unit is inside the CPU, which controls all the activities performed by the CPU. That's why control unit is very important and we should understand more about it. So from gaming and doing some minor calculations, control unit is extremely important in this task. So the functions, existence, the importance we will explain further by my teammates later. So I will now explain about the objectives. First of all, our objectives, the main objective, of course, it is to understand more about the CPU control, and second, how it works, and the third one, to find the aspect of which the CPU control unit affects the most, and then the existence, the importance of its existence, and so on. So suppose that's all from me that I should explain about this. So I will pass to my teammates. Okay. Thank you.
Okay. A very good day I wish to our honorable and respected lecturer, Encik Firdaus. Let me introduce myself. My name is Devaraj and I'm going to talk about the review of a control unit. A control unit, it controls the operation of the computer. A control unit lacks the computer logic unit, memory, as well as both input and output devices on how to respond to the instruction received from a program. Example of devices that utilize the control units includes the CPU and GPU. A control unit works by receiving input information that converts into control signals where are stored to the central processor. The computer's processor then tells the attached hardware what operations are carried out. Furthermore, the control unit functions control sequential instruction execution. It can interpret instruction where the instruction is decoded to deliver what action may require. Moreover, the control unit regulates and controls processor timing. It sends and receives the control signals from other computer devices. The control unit are able to handle multiple tasks such as fetching, decoding, execution handling, and storing results. CU are designed in two ways, which is the hardwire control and microprogram control. The hardwire control can be defined as the design based on a fixed architecture. The control unit is made up of the flow, logic, gates, digital control unit is made, and decoder circuits that are which are digital circuits, and encoder and decoder circuits that are wired in a specific and fixed way. When instruction set changes are required, the wiring and circuit changes must be made. Whereas the microprogram control can be defined as microprograms that are stored in a specific control memory and are based on flowcharts. They are responsible and ideal because of their simplicity. A control unit is used to execute in the form of microprogram which remain control the stores. It gives the arithmetic logic help from the control unit. Okay, thank you for listening to the video presentation review talk. Especially I would like to thank Encik Firdaus for giving us this opportunity on this control unit talk. Thank you very much.
Now we move on to the chapter 2, which is methodology. The method we use in this research is we collecting data from the relevant resources. The relevant resources may be the previous related research reports, information from internet, and also reference book about the CPU design, computer architecture, and computer system. The collected data is then filtered and compared with different resources in order to make a clear and detailed result for the research. By using this method, the collected data is able to process and transform into more useful information for us in this project. After the analyzed result is obtained, we carry on to the discussion, which is we apply the knowledge of computer architecture in this research report. One of the material that we use is internet resources. Most of the information is obtained from the internet, and the diagram and also the figures. Upon the websites where those information is collected are such as Wikipedia, Wikipedia, Google, and also YouTube. Then another resource that we use is the IT reference book. Some of the reference book are fundamentals of computer organization and architecture, system architecture, computer organization and architecture designing for performance, and computer architecture and implementation. The CPU, short form of Central Processing Unit, is just like the brain of the computer. If you understand how it works, then you can understand the computer as well. Let's remove the cover and see what's happened inside. There are lots of different wire carrying informations in the CPU. In every CPU, there is particular wire that turn on and off on steady rate to help keep everything in sync. The wire is called a clock. The clock in this simulation is turning on and off about twice a second. A modern CPU are measured in gigahertz. Giga means billion and hertz means time per second. So the clock in the modern CPU turn on several billion times per second. The speed allows the CPU to do very complicated things quickly. However, the thing that CPU does during each clock tick is very simple. We will look more detail on this in this video later. Now we will zoom back out and put the cover back on.
The CPU in a computer are normally manufactured by Intel or AMD, but the CPU that we are going to talk about today is the Scott CPU. The Scott CPU actually doesn't exist. It is designed by John Clark Scott in a book called But How We Know. This is a great book, and it talks about the component of the CPU and explain how the CPU works in a very clear and simple way. Now, let us flip the CPU to look at its bottom side. You will see a lot of pins. These pins are used to take in information to the CPU and also send the information back out. The CPU is located at the CPU socket on the motherboard. The motherboard allows all the CPU components to connect to each other. So now we plug in the CPU onto the motherboard. And on the right side of the motherboard, you will see a slot to plug in a chip called RAM. RAM stands for Random Access Memory. It contains all the data that is being processed by the CPU. RAM consists of a list of address. Each list of address is a piece of data. The CPU will request and process each piece of data in the RAM. When the computer first running the program, it will send address to the RAM to retrieve the program. The address consists of 1 and 0, which represent on and off wire. RAM doesn't do anything with the address until the CPU turns on the set and enable wire. If the enable wire is turned on, RAM will automatically send whatever piece of data exact to the address to the CPU. The data is processed by the CPU accordingly. Once the CPU is finished processing the data, it then sends another piece of data to the RAM. Turn on the enable wire and get another data from the RAM. This process will repeat over and over again inside a computer. If the CPU is set data to the RAM, it will output an address, then output some data, and then turn on the set wire. The RAM will then overwrite the data to the address with a new data. Although the data in RAM just look like branches of 1 and 0, some of them represent the instruction which tell the CPU what to do, and also number which used to add, compare, or simply process in somewhere. Another thing is address. A particular memory address in a memory in the RAM. The data itself is also an address. For example, this address is used to output a number to an external device, and it has to know the particular address of the device. There are also a letter in RAM, represented by character codes. Now, we look onto the instruction set of the CPU. There will be load, add, store, compare, jump if, jump, in, and out.
So now, let's briefly take a look inside the CPU itself. saw earlier, this is stored inside the CPU. Let's take off this wiring and look inside the CPU. First component is the control unit, which act like a captain of the army. He receives the order from RAM in the form of instruction and break those instructions down into specific commands to other components. Another important component is arithmetic logic unit, ALU for short. The ALU will perform all the mathematical operations inside the CPU, such as additions, subtractions, and comparisons. ALU has two inputs. Let's label them as input A and input B. And soon, here are two numbers and instructions. Now, we will add these two numbers together. The control unit receives the instruction from the RAM and tell the ALU what types of operations to be performed. The ALU will perform the operation and output the answer. Sometimes, depends on the types of operations, the outputs from the ALU can actually be ignored. For instance, for the compare operation, the ALU doesn't output the answers. Instead, it just tells the control unit how the two numbers compare each other. For this, the ALU uses the flag and helps the control unit to decide what to do when it receives the next instruction, like jump, if, which we will see later. Now, let's say the ALU does an operation and give an output. Where did the outputs actually go? Well, the 8 wires coming out from ALU actually runs to the register. A register is just a simple component which used to store numbers temporarily. Register just act like a RAM, except it is inside the CPU and making them faster and more useful for store number temporarily while instructions is being processed. When the ALU sends the output to the register, it won't actually be saved until the control unit turns on the register set wire. Set wire is just like the one we saw earlier at RAM. When the set wire is turned on, register sets whatever number is on the input wire. Once we have the output, how are we going to let it back out? We will need an enable wire that also runs from the control unit to the register. As soon as the control unit turns on the enable wire on, the register will output whatever number is left inside. The output wire from the control unit are connected to the CPU bus. Bus, as we see on the motherboard earlier, is simply a group of wires that connected multiple components inside the computer. On the bus, there are some other registers with their own set and enable wires. This may be other numbers from previous instruction which is already saved inside. So the control unit will turn off the enable wires of the register to clear the bus. The 4 registers on the top are used to store numbers between operations, so then there are outputs wires that go directly back onto the bus. So now we can move number from one register to another register by turning wire on and off. The bus only can carry one number at a time. Because of these limitations, the ALU will use a temporary register from input B. When the control unit is processing an instruction involving the ALU, it will move one of the input to the temporary register. The temporary register don't need an enable wire since it only outputs to ALU and doesn't compete with other registers. The other inputs of ALU comes directly from the bus. The ALU will enable another register, then number will become input A to ALU. The number will stay on the bus until the ALU finishes process the instructions. So now there are 2 inputs for ALU and it's ready to perform an operations. As we saw earlier, the control unit knows what operation to be performed based on the instruction it received from RAM. The instruction itself has its own register called the instruction register, but the inputs wire from the bus would affect this wire since the instructions already set it in the previous step. This register, like temporary register, non-enable wires in just output to the control unit. Based on the instructions, the control unit will tell the ALU what operation to perform. So let's say the operation to process is a compare instruction. For the compare instruction, we're not interested to the number outputs by the ALU. We only want to know how the two numbers compare each other. For that, we use the flag that we talked about earlier. Inside the Scotch CPU, there are 4 flags. We will look at 2 of them now. If A is larger, flag is turned on. The input A is larger than input B. If the inputs are same, the equal flags will turn on. If both flags is off, that means input B is larger. Once the compare instruction is over, we still need flags for next instruction. So we are set to register that only has 4 input and output, 1 of each flags. Once the set wire is turned on in the flags register, the CPU is finished with the compare instruction and the CPU will proceed to perform the next instruction from RAM. Generally, after the compare instruction is jump if instructions. This combination of compare and jump if is very common in the computer programming. Anytime, if there are more than one possible paths to a program, the computer is using this instruction to tell which way to go. So now, let's say the compare instruction is finished. We will tell the RAM ready for the next piece of data. So, inside the CPU, there are another register that is very important, what's called the instruction address register. The CPU uses this register to know when the next instruction should come from RAM. When the control unit is ready for next instructions, it will enable the register wire on the bus. The instruction address will flow to RAM, but it doesn't get directly to the RAM. There are another register called the memory address register, which used to tell RAM what memory address the control unit wants next. Once the instructions address is set into the memory address register, it will automatically send RAMs since the memory address doesn't have the enable wires. The control unit will turn on the enable RAM wire and RAM automatically send back data that address which is in this case is an instructions. That instructions is then sent into the instruction register and the control unit begin processing it. In this case, if is jump if equal instructions, it will check whether the equal flags is on or not. It does that by running one of its wire and the equal flags wire into an AND gate. If both inputs to the AND gates are on, the output wire will turn on as well and triggers the jump. The jumps will retrieve next piece of data from RAM, which happen to be an address, and move it to the instructions register. When the jump in instructions is over, the CPU will process the instructions in that new address. At that new address may be the output, the text like "you guessed correctly" on screen, as now we know that the user guessed correctly. So we have the final 4 wires that connect the CPU, which used to control the external device like monitor and the keyboards. Now let's look on the complete structure that Scotch CPU completely look like. Data move around inside the CPU using bus and stored in register according to how data are going to be used. Each instructions which we have seen can be processed by the Scotch CPU is about 6 clock ticks. Modern CPUs are able to process tons of instructions per clock ticks, meaning to say that the computer that you are using to watch this video is likely process 10 even hundreds billions of instructions per second. This makes the modern CPUs much more complicated than Scotch CPU, but they still fundamentally doing the same things as the Scotch CPU. Let's zoom back out, where we can see all the wire running back out to the pins of the chips. On the right side are the set and enable RAM wires. On the top are RAM address wire, and the bottoms are data wires that run to both RAM and external device. And the left are input and output wire.
Hi guys, it's me again, Eric. So it has finally came to a conclusion. So I'm so happy. So again, I would like to thank my friends for giving, my teammates for giving their best effort to complete this research. So again, I would like to thank Mr. Firdaus for giving us this research, because we have gained a lot of knowledge about the control unit and how the control unit works. Really helps us in our study. So I will start my conclusion now. So in this research, we have used the methodology of by referring to internet and books. Yeah, because it's the easiest way. Sorry, that's why we use it. But it has some disadvantages, because there are too many informations in the internet and books. So really don't know which to take, because different people have different level of understanding and point of views. So there's not big difference between their opinions, but there's some little difference which causes to have some confusions to take which part. So we have held a lot of meetings and discussions to figure out which one we should take into our research. So, and then in this through this research, we have found some solutions to improve the accuracy and veracity of this project. We have found some professionals to have a discussion, to meeting with them to have some comments about our research, to get the viewpoint, the point that we are not doing the mistakes, we are doing the right thing. And then yeah, we also found some commentators to comment about our projects in order to avoid the mistakes that we will have made throughout this project. And again, I think that's all. So okay, thank you. That's our project.
I believe I can fly. I believe I can touch the sky. I think about it every night and day. Spread my wings and fly away. I believe I can soar. I see me running through that open door. I believe I can fly.